Hello everyone, today I am going to discuss some more numerical problem based on the consolidation, and these numerical problems are from the GATE examination. So let's discuss one by one. So the first question we have: an undisturbed soil sample was taken from the middle of the clay layer, that is 1.5 meter below the ground level as shown in the figure. The water table was at the top of the clay layer. Laboratory test result are as when the water content is 25%, compression index 0.5, recompression index 0.05, specificity of solid 2.7, unit weight of sand 17 kN per meter cube, and pre-consolidation pressure of a clay, that is 60 kilopascal. So the pre-consolidation pressure, it means that clay layer already has experienced 60 kilopascal in the past. Okay, so whenever the settlement will occur from when the effective stress will change from some value to the 60, then it will be compression will be in the recompression zone, and after that it will be in normally consolidation zone. So that's things you have to be focused. Okay. So next is a compacted fill of 2.5 meter height with unit weight of 20 kN per meter cube, and again a 2.5 meter height of compacted fill. A compacted soil is filled with the unit weight of 20 kN per meter cube. Assuming unit weight of water, that is given 10 kN per meter cube. Whenever the unit weight of water will be not given, then you have to take the value of 9.81 kN per meter cube. Okay. So find the settlement of the clay layer. So we have to find the settlement. So for the find the settlement, what we should know, we should calculate the initial void ratio, that compression index or recompression index, height of clay that is given. Okay, and initial effective stress at the middle of the clay layer. So let's calculate first. Let's calculate the initial void ratio. So we can apply this equation for the initial condition. That's why we have written E naught. E naught is the void ratio at the initial condition. So we are talking about the consolidation, means degree of saturation will be 100%, and S is equal to 1 we can take. So after putting the value S is equal to 1, G equal to 2.7, and W is equal to 0.25, we can get the initial void ratio 0.675. Right? So after knowing this value of initial void ratio, we can calculate the saturated density of clay layer. So we can calculate using this formula we have, where H is equal to 1. So now we have the saturated unit weight of clay and initial void ratio. So now we can calculate the effective stress at the middle of the clay layer. So why we are calculating the middle of the clay layer? Because effective stress is varying throughout the thickness of soil deposit, or in this case clay layer. So we have to take the average of this effective stress. So for taking the average, we have to find the effective stress at the middle of the clay layer, and that is 0.5 meter below the top of clay layer. So that we get 22.075, because the top layer is sand and that is 1 meter height. So we can write 17 into 1 plus the groundwater table is the top of clay layer. So this half of clay layer is in submerged condition. So we have to take the submerged unit weight. So we can write 20.15 minus 10, that is unit weight of water, into 0.5, we can get the 22.075. So now we can calculate the change. Change in effective stress we can calculate. So when we compacted fill is of 2.5 meter height with unit weight of 20 kN per meter is placed at the ground. So change in the effective stress occurring by filling only. Okay, so we can calculate the what are the pressure is created by the fill. So we can take as a change in the effective stress. So that we can write 20 into 2.5, and we get 50. Are you getting my point? Okay. So now we can calculate the final effective stress or effective stress at the final stage. So initially it was the 22.075 and change will occur, change is occur 50. So now we can calculate the final, that is 72.07, right? So now here you can see that consolidation occur when the effective stress changing from 22.07 to 72. But this clay layer is already had some experience of pressure, pre-consolidation pressure, that is 60 kilopascal in the past. So what we can do? So what we have to consider that 22.075 to 60, this will be occurring in the pre-compression zone, and then after a normal consolidation zone. Okay, so there is a normal compression. So what we can do, we have to be apply a CR from 22.075 to 60, and then we can apply the CC. Are you getting my point? Don't be confused here. Okay, so let's calculate. So see, there is a recompression is shown in the figure where the effective stress changing from 22.07 to 60, and then CC is shown where the effective stress changing from 60 to 72.07. So for this change, the first change 22.07 to 60, we can calculate the settlement and say delta H1. So we can calculate delta H1. So we have all this data. We have the CR value, we have the H node, we have the E node value. So we can calculate, and that is we get 12.966 mm. Okay. Similarly, we can calculate for settlement for the second case, means 60 to 72.07. So we can calculate delta H2. But there is one problem that that in the first case the initial void ratio we have, but for the second case initial void ratio we don't know. So first we have to calculate what is the void ratio at the 60 kilopascal. So whatever the void ratio at the 60 kilopascal would be initial void ratio for the second stage. Don't be confused. For the second stage it would be a initial void ratio. So let's calculate using the CR we can calculate the change. In this case we cannot apply the CC. We have to take the CR. So we can get we have calculated the change, and we have the initial void ratio, so we can calculate the void ratio at the 60 kilopascal, and that we get 0.653. Okay, and this void ratio will be a initial void ratio for the second stage, right? Okay. So now we can calculate the delta H2. So all this data we have, CC and H0 and this E, and then we can calculate, and then we get 24.075 mm. Right? So we can calculate the total settlement by adding these two values. So we can get the 37.04 mm. 37.04 mm. Are you getting my point? See, maybe in this problem, so you can get confused. So why we have calculated the initial void ratio? So initial void ratio will be changed for the first and second stage. Are you getting my point? So initial void ratio we have calculated the E node, that would be the initial void ratio for the first stage, but it is not the initial void ratio for the second stage. Means 62 where the effective stress is changing 62 72.07. So that things you have to be very careful about that, what we have to use and why we are doing this. Okay, and this pre-consolidation pressure of a clay was given 60 kilopascal. So that is also you have to be kept in mind that what is the value and where is the recompression zone or where is the normal consolidation zone or normal compression zone. So that two things you have to keep in mind, and then you can solve the rest question. Okay. So the next question we have a layer of normally consolidated saturated silty clay of 1 meter thickness is subjected to one dimensional consolidation under pressure increment 20 kilopascal. Right? The properties of a soil are given, that is specific gravity of solid 2.7, natural moisture content that is 45%, compression index 0.45, recompression index 0.05. The initial average effective stress within the layer is 100 kilopascal. Assuming the Terzaghi consolidation settlement is, so we have to find the assuming Terzaghi consolidation settlement. So we have to find the settlement in terms of mm. So we can calculate. So all data we have, we can note down. So initial height of soil deposit, that is given 1 meter. A specific gravity of solid 2.7, water content 45%. So all the data we have. So we can calculate the settlement, and that we get 16.08 mm. Okay. And the next question we have, the time for the clay layer is to achieve 90% degree of consolidation is 15 years. Time required to achieve 90% degree of consolidation if the layer were twice as thick, 3 times more permeable, means we can say coefficient of permeability is 3 times, 4 times more compressible. Compressible means the volume of change in the volume can be 4 times. So we can write the MB is 4 times. Okay. So first note down, given is the 90% degree of consolidation, time has taken that 15 years. Then say for the second case where the height is 2 times of H1 means, and K2 there is a coefficient permeability that is 3 times of K1. So this thing was given in the questions. And for the MV2 is equal to 4 times of MV1, means it is in question it was given that 4 times more compressible. More compressible means change in volume can be occur 4 times. Okay. So this relation are given in the question. So in both the cases, degree of consolidation is same. So when the degree of consolidation is same, we can say the time factor would be same, because the time factor it depends only on degree of consolidation. Okay. So we can apply for the both stage. We can take the time factor and we can equate the both the stage. Okay. So what we can do, we can write like this: tau v1 for the first case and will be equal to the tau v for the second case, because the degree of consolidation is say 90% degree of consolidation. So this will be, we can write, and then we can put the value, that's Cv into T by d square. Then we can put the T is equal to 15 for the first case. Okay, and thickness we can write. So see, in this question it is not mentioned that it is the single drainage condition or a double drainage condition. So you can assume both the things, result would be same, right? Okay. So for example, you have taken the single drainage system. So for the both stage, it will be a single drainage system. Suppose you have taken the double drainage system. So in both the stage, it would be a double drainage system. Okay. You cannot do the like in the first stage there is a single drainage system. For the second stage there is a double drainage. No, don't do that. Okay. So now we know that K1 is equal to Cb1 into Mb and gamma W. Already in the previous lecture also I have mentioned this equation. So we can put the value. So we can get this result, and for simplifying we get that coefficient of consolidation for the second stage is the 3 by 4 times coefficient of consolidation for the first stage. So this relation we can put in the above equation, and then we get T, because the dd would be cancelled, that Cv would be cancelled, so we can calculate the T, that is we get 80 years. So it is nothing but just use some relation, and I think in the question it was clear that 3 times more permeable means we are talking about the coefficient of permeability. Twice as a thick means it's talking about the thickness of the soil deposits. So and the 4 times more permeable means 4 times the more compressible means the change in the volume can occur 4 times. So this relation you can keep in mind, and that you can solve. So there is only relation. Okay, so T we get 80 years. Are you getting your point? Okay. So in the next question we have, a saturated clay layer of 5-meter thickness takes 1.5 years for 50% primary consolidation when drained on the both sides, right? Its coefficient of volume change MB is 1.5 into 10 to the power minus 3 meter cube per kilonewton. Determine the coefficient of consolidation in meter square per year and the coefficient of permeability in meter per year. Assume unit weight of water 10 kilonewton per meter cube. So see, in the gate questions, whenever in the mention the unit weight of water is 10, do not calculate by using the 9.81 value. Your answer will be wrong. In the question it is mentioned to take the 10, so we have to take the 10. Okay. So now go for the calculation. So we can calculate determine the coefficient of consolidation. So all data we have, so we can just apply. The 50% degree of consolidation we can apply. See, we can calculate the towing factor. So for time factor is the for 60 for less than or equal to 60% degree of consolidation is pi by 4 into u square, where u is the in the percentage. Okay, sorry, u is in fraction. So we can calculate this way. You can use this value. So we have the T we have, D we have, and see that drain on the both side means this is the example of double drainage system. So we can calculate D is equal to H naught by 2. And by using this relation, we can calculate the CV value, degree of consolidation in terms of meter square per year, and we get 0.8179. Okay. Coefficient of permeability. So now we have to calculate the coefficient of permeability. So we have the CV value, we have the MV value. So we have that we have the one relation which I have discussed in the previous slides. So we can use this relation. K1 is equal to CV1 MV gamma W, where the CV is, we have calculated the CV value, MV value in the given in the question, and unit weight of water we have to take the 10. So by using putting all this value we can get 0.0122 meter per year. So this is the coefficient of permeability. Okay, so this relation we remember always, because this relation we have to be using the question whenever they're talking about the coefficient of consolidation, and we have to find the permeability coefficient, the coefficient of permeability. So we have to use this relation, because this relation is the relation between the coefficient of permeability and degree of consolidation and coefficient of volume change. So we have to remember this formula. Next question we have, a settlement analysis carried out for a proposed structure indicate that 9 centimeter of settlement will occur in 5 years. Okay, so 9 centimeter settlement will occur in 5 years, and the final settlement will be 45 centimeter based on the double drainage condition. Means in the question it mentioned that delta small h is 9 centimeter, T is equal to 5 years, and delta capital H, that is final settlement, is 45 centimeter. Okay, and condition is a double drainage condition. Next, a drained site investigation indicate that only single drainage exists, but in the site it is mentioned only single drainage condition. Estimate the settlement at the end of 5 years for the change condition. Use TV is equal to pi by 4 into E square. Okay. So degree of consolidation we can calculate for 9 centimeter. So we have that equation, delta small h divided by delta capital H into 100. So we can calculate the degree of consolidation. So 9 centimeter, total settlement is 45. So we got the 20% degree of consolidation. So now by knowing this value, degree of consolidation, we can calculate the time factor, and that we get time factor we can calculate. We can use the CV into T by D square. But in the first case, there is a condition of double drainage condition. So we can write Okay, so we can calculate. See, in this equation that in the both field and the laboratory we can say, so that coefficient of consolidation will not change. So we can equate from the both relation, we can equate the coefficient of consolidation. So we can write TV d square by t for the first stage and TB d square by t for the second stage. These both things will be equal because the coefficient of consolidation is not changing, right? Okay, so in this relation we can use this value. So we can write tau v we got some value, so we can write 0.2 into 0.2 square in terms of u square. Okay, so we can put the full the double Dirichlet condition, we can put d is equal to h naught by 2. Time we have 5 years. For the second stage we don't know about the degree of consolidation. Okay, h naught we can write, okay, for the same condition, and 5 time is also taken the 5 years, so we can calculate. See, h naught will be cancelled, so we can calculate the degree of consolidation, that we get 0.1, or we can say in the percentage 10%. So now we have the u value, so we can calculate the settlement. So same relation we can use, delta small h. See, that u we have calculated in the terms of fraction, so we have to use this relation in terms of fraction. We cannot multiply into 100. Suppose it would be a 10%, then we can multiply into 100. So 0.1 is equal to delta h by delta capital H is equal to, so we have the delta h, the final settlement 45 centimeter. So we can calculate the small delta small h means the settlement for the second stage, where the condition of single drainage condition. Okay, so we get the settlement is 4.5 centimeter. 4.5 centimeter. So for we can say that for the same condition, when in the first stage where was the double drainage system, time required for 5 years, and then settlement occurred 9 centimeter. But for the second condition where the drainage condition was the single drainage condition, so at the same condition means the time and this degree of consolidation was different, but the time was same. But for the same time, the settlement is occur 4.5 centimeter. So this the relation we have to use on the data we have given. So this is nothing but just focus what is calculated in this. See, the degree of consolidation. So there is a 2-3 formula I have mentioned how we can calculate the degree of consolidation. First, in terms of settlement, we can calculate also in terms of pore water pressure. We can calculate also in terms of in terms of degree of consolidation. In terms of there is a formula was given pi by 4 into a square, and that we can calculate by using the degree of consolidation. We can calculate the time factor. Okay. So next question we have, a soft normally consolidated clay layer is 20 meter thick with moisture content 45%. The clay has a saturated unit weight 20 kg per meter cube, a particle specific gravity of 2.7 and a liquid limit of 60%. A foundation load will be subjected the center of the layer to a vertical stress increase of 10 kilopascal. Groundwater level is at the surface of the clay. Okay, so this all these data we have, that specific gravity of solid, then liquid limit we have, then saturated unit weight. So estimate the first part, the initial and final effective stresses at the center of the layer. Okay, so center of layer is the 10 meter below the ground level. Okay, and water level is also at the ground level. Okay, and this all the data is given for the clay layer. Second part, the approximate value of compression index means that we have to calculate the CC. The consolidated settlement of the foundation. So we have to find the settlement. So let's calculate the first part. So we can calculate. Assume the unit weight of water is 10 kg per meter cube. Okay, so let's calculate the first part. We can calculate the initial effective stress at point A, that is 10 meter below the ground level, and this is the middle of the clay layer. So we can this clay layer is in submerged condition, so we can calculate the submerged unit weight into their height, and we can write gamma saturated minus gamma W into 10. So we have to calculate the 10 kilopascal. So initial effective stress at the middle of the clay layer is 100 kilopascal. So the final effective stress we can calculate, because change is given in the question, that is 10 kilopascal. So we can calculate the final, that is initial plus change. So we can write 100 plus 10, that is 110 kilopascal. Second case, we can calculate the compression index. So we know that formula of compression index in terms of liquid limit. So what we have this relation where we have to put the liquid limit, we can get the compression index value. So liquid limit is given in the question, that is 60%, and we get CC value, that is 0.45. So next let's go to calculate the second case, that is third part, consolidation settlement of the foundation. So for that we have to calculate the initial void ratio. So we have the G value, we have the water content, we have the S, that is 1, means the degree of saturation will be 100%. So we can calculate the initial void ratio, that is 1.215. Okay. So now finally we can calculate the settlement. So by using this relation, in this relation we have all these data. We have the CC value, that is 0.45. We have the H node, that is 20 meter, this height of clay layer. We have the initial void ratio, that is 1.215. We have the change that is given in the question, 10 kilopascal due to foundation. And we have the initial effective stress at the middle of clay layer is 100 kilopascal, that we have calculated. So by using this, putting this all value, we can get the settlement, that we get 168.2 mm. Okay, so all this question try to solve by using your calculator. Okay, once just note down all this question and try to solve. Okay, thank you.